Okay, thank you very much. So yes, my name's Lewis, and today I'll be presenting a work on satellite-based quantum key distribution in the presence of bypass channels. So this is a large international collaboration that spanned multiple years. And Masood, the first author, had originally hoped to be here to deliver this presentation, but unfortunately couldn't make it. But luckily, I was able to step in. So this work's available on the archive. And to begin with, I'd like to just start with some background and motivation about the specific problem we're trying to solve here, and namely how we've introduced a new security framework which is applicable for satellite-based quantum key distribution. So as we just saw, satellite-based QKD is a promising solution to overcome repeaterless bounds, but as we also saw in the previous presentation, this still comes with significant challenges. It was highlighted that one of these is that it's very expensive to send satellite-based quantum equipment up into space. So one way to tackle this challenge, based off the previous presentation, for example, was to look at the experimental improvements we can make to such things. And in this work, we're going to attack this problem more from the theory side. So we're interested in relevant eavesdropping models to satellite-based quantum key distribution. So what are we looking for in QKD? Of course, we're looking for shared and private randomness. We'd like the same key at the end of the protocol, and we'd like this to look like a random variable to our eavesdropper. And typically, in order to achieve this, we'd like to make some necessary and basic assumptions on any eve, take some experimental observations, and then go ahead and prove the above two properties. So let's actually examine what these assumptions might be and how we might introduce some more practical-based restrictions. So typical assumptions, we'd of course start with things like the secure lab assumption. We might think about the fundamental physics that underpins our eavesdropper or the typical level of characterization of the devices. But the underlying assumption that's going on throughout all of these is that we've assumed Eve has access to the entire channel that separates Alice and Bob, and also that she has unlimited computational resources. So now I want to probe at the question, well, is this actually always realistic? Well, there's some other works that have looked at the latter case, so looking at these computational assumptions that we might start to introduce these restrictions and found that, well, these can be well justified and find improvements. In the same vein, in this work, we're going to look at restrictions that are particular to the satellite-based QKD scenario. And again, the key thing to emphasize here is in both these cases, we're departing from an all-powerful eavesdropper. So what exactly are these restrictions that we're going to introduce in our work? So I'm going to refer to the standard QKD scenario as the unrestricted eavesdropping case. And as I mentioned before, this assumes that Eve has complete access to the channel. So what does this actually imply for a satellite-based QKD setup? Well, firstly, if Eve has complete access to the channel, this implies that Eve is able to receive the entirety of Alice's signal in full if this is being transmitted from the satellite here. And moreover, she can then send whatever else she likes back on to Bob. And apart from that, no other assumptions are made. But practically speaking, if Eve's able to collect the entirety of Alice's signal, this would imply she either has a very large object or is perhaps very close to the satellite. And you might hope that such things are observable. And we could perhaps monitor this link to alert us to such presence of eavesdropping objects. Well, there's one technique out there that allows us to deal with this sort of thing. And that's like, we could introduce a wiretap channel between Alice and Bob. This is based off the assumption that it's typically difficult for Eve to be in space and intercept signals. And hence, the more likely scenario is we have a passive eavesdropper on the ground who just receives some fraction of the overall signal. But the important thing to note here is that this is an assumption that's actually very difficult to verify through experimental observations. And we typically don't want to rely on this in our QKD security proofs. So a key goal of this work is to provide a more generic framework for restricted eavesdropping, which actually has verifiable assumptions. And as I mentioned before, the way that we want to tackle this is through a monitoring of this channel. So one particular example of a type of monitoring we might consider is LiDAR. And using this, Alice and Bob can possibly rule out the presence of eavesdropping objects of a certain size. So what's the implication of this? Well, if we can limit the size of Eve's objects, we can hence go ahead and limit her collection and resend efficiencies. So in the normal scenario, we would consider an ideal channel between Alice and Eve. In this now restricted scenario, we've able to limit her efficiencies, and we can replace this with a lossy channel, where now Eve receives some fraction of the signal and some other fraction is lost. And the same goes between the Eve and Bob link. And now, through some preliminary calculations under some nominal assumptions, it turns out that we can actually provide such bounds. And for example, here we could limit to perhaps like a 20 centimeter max object size. And this definitely implies restrictions, because when we actually parameterize the losses between Alice and Eve and Bob, we find that the previous bounds imply non-trivial upper bounds on the values of these on these transmittants here. So now maybe just to step back, actually, regardless of what monitoring technique we're actually interested in, we still have this interesting scenario where, well, we said that signal from the satellite can reach Eve, or it can miss Eve entirely. It gets lost. But there are some plausible situations where actually this signal could still find its way back to Bob and bypass Eve entirely. So regardless of whatever monitoring technique we've used or we've been interested in, any non-trivial bounds on these transmittants results in a new QKD scenario, which is yet to be studied. And that's this satellite QKD with bypass channels, which I'm going to talk about next. So what actually is a bypass channel? So we can model a bypass channel as, well, we have Alice send some signal. This gets tapped off at this beam splitter, and some fraction of the signal is received by Eve, whereas some other fraction undergoes some quantum operation in this bypass channel and is still collected by Bob. The important thing to note is that whilst this bypass channel is completely inaccessible to Eve, she can't access anything from there, it's also unknown to Alice and Bob. So it's completely uncharacterized, and what Alice and Bob will have to do is, given some experimental observations, they'll have to choose the bypass channel, which minimizes their key rate. So they still need to take the worst case scenario. In scenario B here, we have the kind of standard one which I mentioned before, where now this signal gets lost and it never finds its way back to Bob. And we can compare these two scenarios, and that's our first contribution, is to look at the key rate in these two cases. So we might, for a fixed set of observations, we might first assume that, well, this bypass channel can surely only help Alice and Bob, right? Because there's no signal that's accessible to Eve here. But it turns, so from based off this intuitive argument, we might expect that scenario A always has a better key rate than scenario B. But what we find is actually the opposite is true, and this is actually understandable through the following logic, is that, well, we can actually view scenario B as a special case of scenario A, where this bypass channel is a completely lossy channel. And now, if Alice and Bob want to do their security analysis, in scenario A, they have to do a minimization over all possible bypass channels. Scenario B, they would have to do the same optimization, but the bypass channel is fixed. Hence, in scenario B, we obtain an upper bound on the key rate. And this is important because in scenario B here, this upper bound is actually quite easy to compute, because these transmittants here are trusted, and we can attribute them to the source and the receiver characterization and employ our kind of more standard security proof techniques and obtain an upper bound here. So now I'd like to move on and discuss about what all this actually implies for key rates. So the first example is a continuous variable QKD example, where we consider that the bypass channel is just some lossy channel in this setting. We model the telescope at Bob's end as a beam splitter. We have Gaussian encoder at the transmitter with homodyne detection at the receiver. And then when we need to explicitly model Eve's attack, we consider an entangling cloner attack. And if you recall that I said before, the bypass channel is this uncharacterized quantum channel. Hence, we'll need to minimize the key rate over parameters that are compatible with our observed observations. So that will correspond to this transmittance E to S and E to T here. OK, so if I'll quickly remind you of the two scenarios that we outlined. We had first scenario A, which was the general case where we have to minimize over all possible bypass channels. And we had scenario B here, which was our easier to compute upper bound. And now the first observation to make is that for the reverse reconciliation case, we can now see that if we plot the value of this trusted transmittance here along the x-axis and the secret key rate on the y-axis, The value of eta AE equals 1 would correspond to our normal QKD setup. And for some reasonable amounts of noise, we find that now with a bypass model, we can achieve non-zero key rates, which otherwise would be 0 under normal QKD. The second thing to note is that if we compare these two bounds, the upper bound and the lower bound from our theorem, we find that the upper bound, this scenario B here, is actually a very good approximate to the key rate. And this is very nice because it implies that, well, we can get this fairly easily. Hence, we can get a good approximate for what our key rate looks like without having to do too much extra work on the theory side. For direct reconciliation, we find a similar trend, but only at much lower values of eta AE. Okay, now to consider the discrete variable case. So we consider BB84 with single photons and also phase randomized weak coherent pulses. And in this scenario, we can treat the channel between Alice and Bob as a photon number channel. So Alice probabilistically sends some n photons down the channel, some fraction m are received by Eve, and we then secure secret key bets when Alice sends exactly 1 photon. But now we also have this interesting scenario where if this eta AE value is kept small, some fraction of the photons can go down the bypass channel, cause a detections at Bob's end, and not flow through Eve at all. And it turns out we can capitalize off this. So for small values of eta AE, we can move to large photon intensities. And as a result, we find that the majority of the signal is flowing through the bypass channel and being detected at Bob's end due to the large efficiency. We don't need to worry about photon number splitting attacks so much. And we can actually then go and achieve rather large key rates. If we go ahead and compare this to the single photon calculation, we no longer possess this advantage to go to large photon numbers. We're only restricted to single photons, and we don't see this advantage. This is an interesting observation to make, because typically we'd all assume that BB84 is perhaps the most optimal QKD protocol to run, but actually in this bypass model, it turns out it's certainly not the optimal choice. And then this is also the behavior we'd expect to see in a wiretap channel I mentioned before, but the key thing now is we've now got a more monitorable assumption. Finally, I'd like to talk about the ongoing work that's come out of this and was included in here, is that the application of more versatile numerical security proof techniques to the discrete variable case. And there's some nice motivation for doing this. These numerical techniques have shown to be more versatile, practical, and they can also tighten up the bounds in some cases. And a nice example of this is in the single photon case. So if you recall in the previous slide, I showed you there was no visible improvement yet in the bypass model. Well, now if we use the versatility of the numerics, we can model, for example, a detector efficiency mismatch at the receiver, and we now find we can achieve those positive rates, which would otherwise be 0 in the non-bypass standard QKD setting. Okay, so to summarize, the take-home message is, in this work, we've introduced and studied a new setting, which we called QKD with bypass channels, and we've shown that it implies improvements for satellite-based QKD implementations on the theory side. We considered 2 examples, one of which was an upper bound on the other, which was the more general case, and we showed that, well, we argued that this upper bound was easy to calculate, and we also showed that this upper bound is a good approximation to the key rate with CVQKD and reverse reconciliation. We also showed that the bypass model can achieve non-zero rates, which would otherwise vanish under normal QKD scenarios, and we found similar results for the discrete variable case. For future work, we'd like to keep working on this numerical approach and see what else is possible with the bypass channel. It's also, our results are asymptotic at the moment, so it's an interesting question as to how the bypass model behaves under finite statistics. We also found that reverse reconciliation was very advantageous in the CV case, so does this also hold for the discrete variable case? And lastly, more speculative questions of what other scenarios does the bypass channel apply to? For example, could there be non-prepared measure QKD scenarios or more unconventional security work? So with that, I thank you for your attention, and we welcome any questions.
Take some questions.
Very nice talk. I have a question. I think I'm still confused as this picture of the A and the B. You said that's the secure key rate in scenario B. It's higher than scenario A, right? That's what you claim.
Yes.
But can we just assume that for example, in scenario A, can we just assume that the bypass channel really go through Eve, then isn't that the for Eve get more information, then the key rate will be lower?
Sure. So yeah, maybe I can elaborate a bit more about this. So the claim is that for a fixed set of observations, when we compute the secret key rate over the bypass channels compared to where, again, we have the same amount of loss of transmittance here, that the secret key rate in A is a lower bound on that in B. And maybe an intuitive way to perhaps understand this is that well, you can argue it from the mathematical point of view, which is what I tried to do first, which was that, well, in this scenario, with all things being equal, we have to minimize over the possible bypass channels. And in scenario B, you can imagine that one such bypass channel in our minimization is the completely lossy channel. And with that completely lossy channel, we arrive back at scenario B here. So it's kind of, we've replaced this minimization with an upper bound on the true minimization by ensuring a completely lossy channel here. Maybe a more intuitive way to think about it is that in scenario A here, if some of the signal is flowing through the bypass channel and being collected by Bob, this actually allows Eve to be a bit more malicious because she can keep more signal for herself whilst maintaining the same amount of total loss in the signal, whereas here she has to necessarily transmit more signals to Bob in the scenario B.